Hey everybody, it's Ripley back again. We're in 12.2. We're going to talk about arithmetic sequences. Arithmetic sequences are special sequences. They're not just some standard issue sequence that you're pulling the range off of a function whose domain is the positive reals, or excuse me, the positive integers. An arithmetic sequence plays like this. What it is it's still a sequence, so it's still one of these guys. All right, and it's going to have a sub 1 and a sub 2 and a sub 3 all the way out to a sub n. But there's a relationship between these elements. Elements are the things that go in sets. And it's referred to as a recursive relationship. And I'll define that here in just a sec. In other words, a recursive relationship. Recursive relationships mean that there is a relationship whereby for any value from a sub 1 to a sub n, I can go to the element immediately before, or maybe 2 before, maybe 3 before, to find this value. Okay? So in other words, a sub 3 is tied to a sub 2. A sub 2 is tied to a sub 1. A sub n is tied to a sub n minus 1. All right? Now, here's the way it works. They're defined recursively by something called a common difference. Common difference. I need to figure out this tablet. If any of you guys can figure out how to make this thing not lag, let me know. All right, common difference, which is what we're going to refer to as D, is simply a number. All right, now watch how this works. A sub 1 is just a sub 1. Your author refers to it as A, but I'm going to let a sub 1 be a sub 1. A sub 2 is equal to a sub 1 plus this common difference. And this difference is just an element of the real numbers, preferably not 0, because then this is a decidedly boring problem. All right? A sub 3 is equal to a sub 2 plus d. That's the common difference, but think about that. We know that a sub 2 is equal to a sub 1 plus d, right? So this is going to be a sub 1 plus d plus d, aka a sub 1 plus 2d. Think about a sub 4. A sub 4 is just a sub 3 plus d, but I know that a sub 3 is a sub 1 plus 2d, right? So this is just a sub 1 plus 2d plus d, affectionately known as a sub 1 plus 3d. Now you may already be seeing a pattern here. Look at the pattern. A sub 4 equals a sub 1 plus 3d. A sub 3 is a sub 1 plus 2d. Somebody put a gun to your head in the park and you had to guess what a sub, as opposed to 3, a sub 5 was. What would your guess be? You guessed right. A sub 1 plus 4d, which implies that a sub n, any n, can be tied or can be found as long as I know what a sub 1 is, and then plus what? It's going to be n minus 1 times d. Right? Now, I said that this was a recursive relationship, so we got to make sure that we kind of put a bow on that. What do I mean by that? Well, it's recursive because I know that a sub n is equal to what? A sub n minus 1, the one immediately preceding it, plus d. Or, with a puff of algebra, I know that a sub n minus a sub n minus 1 is always equal to d. So if I have a sequence, let's say that a sub n is defined as such. Now, I don't know, 2, 7, 12, 17, 22, ... Right? Well, what do I know? I know that a sub 1 is equal to 2. I know that d, well, how did I get from hither to thither? Hither to thither. Hither to thither. I added 5. This is plus 5, plus 5, plus 5. Now here's a problem. If this relationship, if this difference between elements in the sequence changes, I got big troubles. Oh, suppose I should put an a sub in here. I got big troubles because I'm no longer in an arithmetic sequence. This has to be true for all values. So I know a sub 1 equals 2. I know that d equals 5, and no, I'm done. All right? So that was pretty easy. How about if I want to know, well, if this, remember this is n equals 1, this is when n equals 2. What if I want to know what a sub 17 is? Right? And I don't want to have to go through this process 17 times. Well, I just go a sub 1 plus 16. What am I doing? 16 times d, right? Just use my equation. It's the easiest thing in the world, which is 2 plus 16 times 5, affectionately known as 82. I'm all set. Nothing to it. All right? Now, what if I want to know, let's see, let's come up with an interesting problem. How about this one? What if I know that a sub 3 is 4? There's a specific sequence whose third term is 4, and a sub 6 is 21. All right? Now let's make it a sub, let's make this 71, so it's less pretty. 71. All right? I want to know what a sub 1 and d are. What are they? Well, how can I figure that out? Can you think about it? Well, let's think about this. I know that a sub n is equal to what? It's always equal to a1 plus n minus 1 times d. Agree with that? Now, I don't have very much information here, do I? I've got two sort of ostensibly randomly picked elements in this set of elements. But I do have this piece of information. Doesn't that imply that a sub 3 is equal to a sub 1 plus 2 times d? Remember, I'm looking for a1 and d, correct? And I know that this equals 4. I also know that a sub 6 is equal to a sub 1 plus what? 5 times d, which is equal to 71, right? Look at that. I have two equations with two unknowns. Hey, we just dealt with systems of equations, only this one's linear. There's only two variables, two unknowns. So if I subtract these, I'm simple confoque, you guys know this, so I'm going to subtract the top from the bottom. The a's, how should I denote this? No, let's do it like that. I'm going to subtract this guy from this guy. My a1s cancel. I end up with 3d, because 5d minus 2d, last I checked, was 3d. Ooh, how fancy. And then what do I end up with? 67? So d equals 67 thirds. Well, once I have d, how hard is it to find a1? Just plug and chug, right? So this implies that a1 plus 2 times 67 thirds is equal to, I know I'm going to be dealing with thirds, so I might as well put this in as 12 thirds, because I'm trying to stay out of my own way. I also always use the smaller of the equations, the smaller the numbers, the ones without negatives, all that jive. It typically makes my life a heck of a lot simpler. Okay? So let's see, what do I end up with this? 134 thirds. So A1 plus 134 thirds equals 12 thirds, which implies that A1 is equal to 12 thirds minus 134 thirds, which is equal to what? Negative 122 thirds? Negative 122 thirds, which isn't reducible because 3 doesn't go into 122. Now, that may freak you out. You may say, well, Ripley, what the heck? Let's see. So you're telling me that my first term, A1, is equal to negative 40 and 2 thirds? Are you kidding me? Well, I didn't say that there was any rule that A1 always had to be positive. A1 can be negative. Remember, A1 is the range of the function. The domain of the function is the positive integers, but the sequence is defined by the range. That's what goes in. Right? Kind of fun. Something to think about. Now, I got a question for you. What happens if we sum these up? Let's have some fun. How about S sub n? All right, so we're going to add them up. Now, when you're dealing with these types of things, you'll often see S sub n, or you'll see the sum, this sigma notation. Okay? I'm going to use S sub n because your author uses it, and I use it again in calculus. All right? So I want you to be sort of flexible in terms of what you see. All right? But I'm going to sort of interchange sigmas and S sub n's. All right? So let's look close. I know that the S sub n, if I sum up, you know what? I'm being just a little bit lazy. Let me change my color here. and I'm going to do this, and I'm going to do this. I'm sorry, you guys. What about the sum of an arithmetic sequence? Sum of an arithmetic, because we did it before, right? We were adding all sorts of stuff up. Sequence. So S sub n, now it's real simple. It's simply going to be a sub 1 plus a sub 2, just like before, plus a sub 3 plus a sub 4 plus dot 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 plus a sub n. This could be written as the sum as k goes from 1 to n of a sub k, right? We're not afraid. Now, think about this. How do I do this? Because there's no way I'm going to kick over here.